In this video, we're going to discuss how to perform the chemical equilibrium lab. Now, while watching this video, please take careful detailed notes. Each student will be expected to be able to correctly prepare all their solutions and all the calculations without additional help. So please pay attention, and if we go too fast at a certain part, please pause and rewind the video. So let's get started. First of all, we know that an equilibrium constant is the ratio of products to reactants for a given reaction at equilibrium at a given temperature. And you can see the general formula for an equilibrium constant here. Now, the magnitude of the equilibrium constant gives us some information about the reaction that we're studying. If the reaction has a large equilibrium constant, that means that when the reaction has reached equilibrium, there's a lot more product relative to the amount of reactants. And if a reaction has a small Kc value, that indicates that once the reaction's reached equilibrium, that the ratio of products, you're going to have a lot less product relative to the amount of reactant. So we say that that reaction would proceed very little to the right in order to reach equilibrium. An equilibrium constant for a given reaction at a given temperature is a constant value. And that's important to think about. So that tells us that no matter what reactant concentrations we begin our reaction with, the ratio of products to reactants will always be the same at equilibrium for that reaction at a given temperature. So for this lab, we're going to calculate the Kc value for this chemical reaction. Iron 3 plus thiocyanate yields iron thiocyanate, excuse me. And we'll allow this to come to equilibrium, which will occur in just a couple of minutes, and we'll be able to calculate the equilibrium constant for this. Now, we also want to note that what we see here is the net ionic equation. The solution we're actually going to be using for iron, we're going to be using iron nitrate, will be our source of iron 3, and potassium thiocyanate will be our source of thiocyanate. So we're just looking at the net ionic here. So we will perform this reaction using different initial concentrations of the iron 3. So we'll perform this reaction several times. Each time we perform the reaction, we'll start out with a different concentration of iron 3, and we'll calculate the Kc value for each reaction. We would expect that each reaction should have the same Kc value. Because again, it doesn't matter what initial concentration we start with, the ratio once we reach equilibrium should be the same. So we'll perform 6 experiments. So we'll perform this reaction 6 times. Each time we perform the experiment, we'll have a decreasing concentration of the iron 3. We'll keep the same concentration of thiocyanate, and again, we'll calculate the equilibrium constant for each of these 6 experiments that we're performing. And then we'll compare the Kc values for the experiment and hopefully confirm that they should all be pretty much the same. So I want to talk about this video or divide this experiment into 3 parts. The first thing I want to discuss is how to make the iron 3 dilutions, and we'll use volumetric flasks for that. So we have to have decreasing concentrations of iron 3. So we'll discuss how to do that first. Once we have our iron 3 dilutions made, then we'll have to combine those with the thiocyanate in our test tubes in order to perform the reaction. So we'll show you how to do that. And then once we have these 6 reactions performed, we'll need to measure the absorbance of our product at equilibrium, our iron thiocyanate, in each experiment, and we'll also show you how to calculate the equilibrium concentrations of all species and then the Kc values. Okay, so these are the 3 parts we want to talk about. So let's start out by showing you how to make our iron 3 dilutions. So we're going to have our stock, and then we're going to make 5 dilutions from our stock iron 3 nitrate solution. So let's go over how to do that. So the first thing we're going to do is we're going to take 10 milliliters of our stock. You can see our stock iron 3 nitrate here. Oops, that shouldn't be there. Our stock iron 3 nitrate should be about 0.02 molar. You'll get the actual concentration when you get to the lab. And we're going to take 10 milliliters of the stock and we're going to put it into a 25 ml volumetric flask. And we'll call this first flask dilution 1. So once we add 10 mils of the stock into the flask, then we're going to add water, deionized water, until we get the volume up to the 25 mil mark. Now we've prepared our first dilution, and we need to calculate the concentration of this first dilution. To calculate any dilution, we generally use the M1V1 equals M2V2 formula, where M1, that's the volume of the stock, since we use that. We use 10 milliliters of the stock. We want to figure out X, which is our final molarity of our dilution 1, and our final volume, we said we brought it up to 25 mils. So if we calculate that, the concentration of dilution 1 should be about 0.008 molar. Okay, now that we've prepared dilution 1, let's use some of dilution 1 to make a second dilution. Again, we want to make several dilutions where we get more and more dilute with our iron 3. So we're going to do kind of the same thing, except instead of using the stock, we're going to take 10 milliliters of dilution 1, which we just prepared, and we're going to put that into a 25 ml volumetric flask. Then we're going to add water until we get up to the 25 mil mark. So now we've taken some of dilution 1 and we've diluted it to make dilution 2. So let's calculate the molarity of dilution 2. Again, use the same formula, but our M1 here is not the stock. We did not use the stock, we used dilution 1. So let's use the molarity of dilution 1. We took 10 milliliters of dilution 1, put it into dilution 2, and our final volume was 25 mils. So solve for X, and that gives us the molarity of dilution 2. Now we're going to use dilution 2 to make a third dilution. Same process. We're going to take 10 milliliters of dilution 2, put it in a volumetric flask, bring it up to 25 mils with deionized water, and now we've prepared our third dilution. Calculate the molarity of the third dilution, same thing, except our M1 is going to be the molarity of our dilution 2, since that's what we used in our dilution. So we should be able to calculate the molarity of dilution 3. We'll repeat this process to make dilution 4 and dilution 5, and you want to be sure you calculate the molarity of dilution 4 and dilution 5, as I just showed you. So when we're finished, we should have our stock, so we'll have some of the stock, and then we'll have prepared 5 dilutions of iron 3 nitrate. Each, as we go from left to right, we get progressively more dilute. So we'll use these to make our reaction mixture. And that brings us to the second part. Now we want to combine our iron 3 dilutions with the thiocyanate in our test tubes in order to perform the experiments. Okay? So here we're going to actually perform the experiment. So we're going to prepare 6 test tubes. We want to prepare 6 different experiments, so we need 6 test tubes. In each test tube, we're going to add 5 milliliters of the stock thiocyanate. We're not making any dilutions of this, so 5 mils of the stock thiocyanate. And to each test tube, we're going to add 5 mils of one of our dilutions, our iron dilutions that we have just described how to prepare. So it should look something like this. Let's say we have 6 test tubes. We're going to put 5 milliliters of the stock potassium thiocyanate into each. Okay. Now, to the first test tube, or to each test tube, we're going to add 5 mils of one of our iron dilutions that we made using our volumetric flask. So let's go over that briefly. For the first test tube, we're going to add 5 mils of the stock. So we're going to take 5 mils of the stock thiocyanate, the stock iron nitrate, and we're going to put it in there into test tube 1. So those will react. But we have to calculate the concentration of iron and thiocyanate in this test tube, because when we mix them together, we actually have one more dilution. So these are the concentrations that we're actually going to use in our calculations. So let's look at that. Okay. So we're going to use M1V1, M2V2 to calculate the concentration of iron in the test tube. Okay. This initial concentration, the concentration we're about to calculate, is what we're going to use to help calculate our Kc values, as we'll see. So this is very important. So let's show you how to do that. Let's take M1V1 equals M2V2. Now we put 5 mils of the stock. So our stock concentration is 0.02. We put it in there with 5 mils of the thiocyanate, right? So our final volume is 10 mils. So when we combine these two together, we're actually having another dilution. So 5 mils of the iron stock is combined with 5 mils of the thiocyanate. That gives us our V2, and we can solve for X, which is our concentration of iron in our test tube, and it should come out to about 0.01 molar iron. Now, with the thiocyanate, we also have to calculate the working concentration of thiocyanate in this test tube. So what we're going to do here is use the same formula, M1V1 equals M2V2. This is my stock concentration of thiocyanate, and we added 5 mils already. And when we added the iron, it diluted the thiocyanate to 10 mils. So my V2 is 10 mils. And we solve for X, and we get our initial concentration of iron thiocyanate. So please take a minute, review those calculations, and be sure you're absolutely clear on how to calculate the initial concentration of iron and the initial concentration of thiocyanate in these test tubes. Now we have to move on to test tube 2. We're not going to add the stock to test tube 2. We're going to take some of dilution 1 that we prepared previously and add 5 mils of dilution 1 of the iron into test tube 2. Now, again, same as before, when we add 5 mils into the 5 mils of thiocyanate, we're diluting it. So we need to calculate the concentration of the iron and the thiocyanate, just as we did before. Okay. Now, we're going to move on to test tube 3. We're going to take 5 mils of dilution 2 and add it to test tube 3. And then we're going to use our M1V1, M2V2 to calculate the concentration of iron here. And then we're going to use the same formula to calculate the concentration of thiocyanate. So as we're going, we're calculating our our initial concentrations of iron and thiocyanate in each test tube. Okay. Then we take some of dilution 3 that we prepared earlier, put it into test tube 4, calculate our concentrations of iron and thiocyanate, use dilution 4, add that to test tube 5, and then calculate our concentrations, and then add dilution 5 to test tube 6. So again, be sure, take your time, review the video, and be sure you're absolutely clear on what we're doing here, because these steps here can be a little tricky, and you will be expected to do these calculations. So now let's look at how to calculate our equilibrium concentrations of reactants and products, and also calculate Kc for each experiment. So we have our 6 experiments, our 6 reaction mixtures, and we're going to take a little bit of each of these reactions and measure its absorbance using a spectrophotometer. Now we'll go over how to use the spectrophotometers in class, but we're going to get some very important information from our spectrophotometers. The absorbance data that we get will allow us to calculate, it's related, the absorbance is related to the equilibrium concentration of iron thiocyanate, which is our product. So we're actually measuring, essentially indirectly, the concentration of iron thiocyanate at equilibrium by recording the absorbance values. So before we can do the calculations, we have to look at make an assumption. For the first test tube that we made up, and only the first test tube that we made up, our initial concentration of iron is much, much greater than the initial concentration of thiocyanate. It's well over 1,000 times greater concentration. So therefore, we can assume that for test tube 1, all of the thiocyanate is used up, and it's all converted to make our product iron thiocyanate. So thus, the equilibrium concentration for thiocyanate for test tube 1 only is equal to 0. and the equilibrium concentration of iron thiocyanate for test tube 1 will equal the initial concentration of thiocyanate. Let's look at this using an ICE table. So we have our reaction and our initial concentration of iron 3, that's what we calculated in our test tube, so look back at that calculation. Our initial concentration of thiocyanate we have here. Again, that's the concentration that's in test tube 1. We already showed you how to do that calculation. Our initial concentration of iron thiocyanate should be 0 initially. Since this is 0, we know our reaction will proceed from left to right to reach equilibrium. So our change will be minus X on the reactant side plus X on the product side. Now we've made the assumption that for test tube 1 only, all of our thiocyanate is converted into iron thiocyanate. So our equilibrium concentration of iron thiocyanate is equal to the initial concentration of thiocyanate. And also, all of our thiocyanate is used up, so our equilibrium concentration of thiocyanate is 0. We can calculate the equilibrium concentration of iron by taking the initial minus X, where X, of course, is what we have here, our equilibrium concentration of iron thiocyanate. Now, because we have a 0 value here, we're not going to be able to calculate a Kc value for test tube 1, but we will use this data. We'll use test tube 1 as a reference to calculate the equilibrium concentrations in the other test tubes. And we'll show you how to do that now. So let's look at test tube 2. We calculated the initial concentration of iron and thiocyanate in test tube 2. Look back at those calculations using M1, V1, M2, V2. Our initial of iron thiocyanate, 0. Our reaction will proceed from left to right, so we have our minus X on the reactant side and our plus X on the product side. Now we cannot assume that all of the thiocyanate is converted into iron thiocyanate here. We can't make that assumption. We have to use our spectrophotometer data. So we want to get this value here. We want to figure out what is the value at equilibrium of the iron thiocyanate. So how do we do that? Well, we use the Beer-Lambert law, and we set A1 divided by C1 equal to A2C2, and we solve for C2. Now let's look at what these variables represent. A1 is the absorbance in test tube 1, and we measure that experimentally. C1 is the equilibrium concentration of iron thiocyanate from test tube 1. We just showed you how to do that in the previous slide. A2 is the absorbance of test tube 2, and C2 is the equilibrium concentration of iron thiocyanate in test tube 2. So when we solve for C2, we're solving for the equilibrium concentration of iron thiocyanate, in this case in test tube 2. So here you can see it again. A1, we know what that is experimentally. C1, we showed you how to calculate that. A2, we can measure that experimentally through the spectrophotometer. And C2, we calculate that as we just showed you using the formula in the previous slide. So we should be able to calculate the equilibrium concentration of iron thiocyanate. And that value will also be equal to X. So then we can calculate the equilibrium concentration of thiocyanate by taking X, which we know now, minus, or the initial concentration of thiocyanate minus X, and the initial concentration of iron 3 minus X, and therefore we should be able to get our equilibrium concentrations for all of our species. So remember, our equilibrium concentration of iron thiocyanate is our X value. Okay. So now that we know X, we can calculate our equilibrium concentrations. Once we have all our equilibrium concentrations, those are what we use to calculate our Kc, not initial, but equilibrium. So we plug those into our expression here and solve for Kc. Okay. We'll do the exact same process to get the Kc values in test tube 3, 4, 5, and 6. For all of those, we're going to use the same A1-C1 ratio. So in all our calculations, we use the absorbance of test tube 1 divided by the concentration in test tube 1, and we set that equal to the absorbance for whatever test tube we're studying, and this one 3, divided by the concentration of iron thiocyanate at equilibrium for test tube 3. And again, we solve in this case for C3, which is our equilibrium concentration of iron thiocyanate, and that's our X, and then we can calculate these. Okay. For the other test tubes, same formula, we just use A1 over C1 is equal to A, whatever test tube we're looking at, divided by C for whatever test tube we're looking at. Okay. So please take some time, take careful notes, be sure you understand exactly what you're doing, and particularly calculations. These can be kind of tricky. There's a lot of steps. That's why I took the time to make out the video. So please take some time to be sure you understand that before we do this lab.